Okay, so in this lecture, we will talk about true and apparent distribution volume. It's about like a drug distribution volume. So in the body, like where does the drug goes? Like how much space does the drug take? And before we do that, let's review the discussion we discussed earlier in in, in a lecture early to this course. We looked at fluid compartments and their approximate volumes for 70 kilogram man. So we said that in total, the fluid volume in the body is about 40 liters. And in the plasma, there's only 3 liters. So this is the plasma. So is the total concentration we are looking at. And the drug can also go to interstitial space, which is go across the capillary wall. We discussed the filtration in our early lectures. So interstitial and the plasma collectively they are extracellular fluid, and they combine and contribute to 15 liters of fluid in the body, and the intracellular is 25 liters in the body. So you know that if a drug after taken, if it goes to the plasma and then it goes to the interstitial space, then it also goes to the intracellular space, goes into the cell. Then the distribution of the volume, the true distribution is 40 liters. If a drug is confined exclusively to the plasma, then its true distribution is 3 liters. So let me put this way. If a drug exists in plasma and moves through the interstitial space, then the true distribution, well, it's not 100% go to the interstitial space because there will still be drug in the plasma. Then the true distribution volume is 15 liters. So if a drug is confined exclusively in the plasma, so if a drug is confined exclusively to the plasma, then the true distribution volume is 3 liters. Now you get an idea of what does true distribution mean. And depending on the drug, like some drug, maybe they just cannot leave the capillary wall because maybe they are too big to go to the wall. Or if they can, they are permeable to the wall, then they are not permeable to the lipid membrane, and then they cannot go to the cell. So for drugs that can go into the cell, that means it's lipid membrane soluble, or they have other mechanisms to enter into the cell, then it is also in the intracellular space, then it will be the true volume will be 40 liters. So that's the idea. And the rate at which a drug reaches different compartments is dictated primarily by 2 physiological like parameters. The first is blood perfusion rate and the capillary permeability. So the true volume distribution Depends on blood perfusion rate and the capillary permeability. The capillary permeability. So blood perfusion rate refers to the volume of blood delivered to a tissue per unit of time. And this is like we have learned that it contributes to the convection, and then that's why it is important for the transport of drugs to different parts of the body. Tissues with higher perfusion rate usually gets more drug in an effective way. Poorly perfused tissues, they usually don't get much of this drug. Capillary permeability refers to the ability of drug to traverse the capillary wall and entering the interstitial space. So this is highly influenced by the molecular weight, polarity, and how they are able to go through lipids. So lipid-soluble drugs can diffuse across capillary membrane, and in that case, the rate-limiting step for the distribution is often the rate of blood flow to the tissue. And in that case, it's called a perfusion rate limited. So that means if the drug is soluble in lipids, means they can easily go across lipid membrane. Means the lipid membrane step isn't a barrier. So then the barrier would be like perfusion rate limited, because it can easily it goes to the it can go across the membrane with so this mechanism is like, how to describe it, this diffusion, maybe let's call it diffusion. Yes. So if you have a drug concentration from one compartment to another compartment, as we learned that either it can go through diffusion or convection. So in this case, it's easily go across the lipid membrane, then means diffusion is not a problem, or diffusion is efficient. Maybe that's a better way to explain it. So that means this is perfusion rate limited distribution, because perfusion now become a critical parameter. Perfusion rate limited distribution. The other hand, if drug is not permeable to capillary, then they cannot like diffuse easily. This is called diffusion rate limited. So this is just telling you like the mechanisms that for drugs to go across the capillary wall and go into different compartments that constitute the true distribution. Now let's look at what does apparent distribution mean? Apparent. It's good to get the true volume. However, as you can imagine that it's hard to measure, like it's hard to like stick a sensor to the interstitial space and like poke the tissue and say, okay, let's measure whether the drugs enter into this space. It's not practical. So the practical way is okay, maybe people clinically they can measure the concentration of drug in the blood, in the plasma, and use that as an approximation or estimation. So this is called apparent distribution volume. The apparent it is defined by this volume, not velocity. So volume V is defined by A drug divided by C total. A drug is the total amount of drug in the body. Total amount. So usually it's in milligram. And the C total, as we said before, total drug concentration is floating bound and unbounded in the plasma. So they're usually in like milligram per liter. So then this ratio give you a volume in liter. And you can see that this is a volume that only depends on the drug concentration in the plasma. Then the apparent volume can be either an overestimation or underestimation of the true volume, depending on the concentration of the drug. So V apparent can be an overestimation or underestimation of the true volume distribution. So if the concentration everywhere are similar, in different compartments are similar, then it may give you a good approximation. However, if a lot of drug like goes into the cell or interstitial space, that means the concentration in the plasma is actually very low. Then if you use a drug divided by a very low number, then you would get a larger volume, apparent volume. The volume you get may even be larger than the body, the entire human body, which is non-realistic. So depending on like where the drug goes, this can vary a lot. And there are people try to figure out better ways to estimate the apparent volume instead of just using the total drug in the body divided by C total. And we may talk about this later. And now let's look at an exercise. So a patient is administered 800 milligram of a drug. This drug is lipophilic. That means the drug is able to go through cellular membrane. After 1 hour, the plasma concentration is measured at this value. Assume negligible metabolism and excretion during this period. Calculate the apparent distribution volume. And based on your result, describe the likely distribution characteristics of the drug, including the extent of tissue binding and the potential compartments involved. So think about if the apparent volume doesn't seem to be intuitive or understandable to you, try to think about different scenarios, like if the C concentration in the plasma is much less than the concentration in the interstitial space, how does the apparent look like? On the other hand, if C plasma is much higher than the concentration in the interstitial space, what does the apparent look like? So do some of these like thought experiment on your own, and then revisit this problem and try to figure out how do you interpret this result.